Welcome to OStats, a platform for short statistical hacks. This video will cover correlation. One of the first things that you'll learn about correlation is that it doesn't equal causation. What this means is that we're saying nothing about cause and effect. Correlations are completely symmetrical, so a correlation between A and B is the same as a correlation between B and A. If significant, we expect them to move in coordination with each other. A positive correlation will move in the same direction, whereas a negative correlation will move in an opposite direction. Either way, they change at a constant rate. We can measure correlations using the Pearsons correlation coefficient, which is expressed as R. We should expect the correlation to be linear, and the strength of the correlation is on a scale from -1 to 0 to +1. The Pearsons correlation coefficient can only be estimated using variables that are either interval or ratio. You can use the Spearmint correlation coefficient if your data does not meet rules of normality, meaning the data is not normally distributed, or your data is ordinal, so not interval or ratio. This is a non-parametric test. More specifically, it is the measure of the strength of a monotonic relationship between paired data. It is also measured on a scale of 0 to plus or minus 1 and is indicated by the S rather than the R. Looking at this conceptually, the strength of correlations fluctuate much more in smaller samples, and as much as correlations can be non-significant or low, they can be too high, which raises concerns about multicollinearity or singularity when variables are perfectly correlated. This makes it difficult in the next step of regressions to determine the unique contribution of each variable. It is possible that one variable is a proxy measure for the other. So ultimately, correlation is used to quantify the strength and direction of the linear relationship between two variables, where a change in one is accompanied by a change in the other, either in the same or opposite direction. But this is not to be confused with regression. You cannot use correlations to predict one variable using another, or to describe the association between variables as you do in regression. Of course, there is a possibility that one variable might cause the other, or the second variable might cause the first, or they could both be caused by something else, or it could be random chance. So you should always have a theoretical reason for considering a correlation, but these are not the aims of correlation testing. The population correlation coefficient is really what we want to measure, at least in an ideal world. This is represented by the Greek letter rho, but we cannot measure the entire population, so we measure the sample correlation coefficient as the rho estimate. The larger the sample size, the more confident you can be that the R is a true representation of the rho, or, said another way, the more confident you can be that the sample is a true representation of the population. The Pearsons correlation coefficient effect size can be small, medium, or large, but it is often referred to as weak, moderate, or strong. An effect size of 0.10 is small or weak and explains 1% of the total variance. An effect size of 0.30 is medium or moderate and explains 9% of the total variance. And an effect size of 0.50 is large or strong, as it explains 25% of the total variance. But it is also important to note that this scale is not linear, so 0.30 is not 3 times larger than 0.10. The R can be reported as R equals 0.45, with a significance or a p-value of less than 0.001. A less common method also reports a number of observations, or the n, here shown as 757. The square of the correlation coefficient indicates the proportion of variance explained in one variable by the other, and you times that figure by 100 to get the percentage of variance explained. And in the first instance, that amounts to 20.25%. In the second instance, that amounts to 4.41%. Scatter plots are a great way to visualize linear correlations. There are no exacts here, but they give you a general idea of what the strength and direction of correlations look like graphically, in all cases against a linear line of best fit. You can get misleading correlations because of nonlinear and curvilinear data, but spurious data is especially problematic because correlations are very sensitive to extreme values. And of course, independent distributions indicate no correlation at all. And that's OStats. If you like this video, consider subscribing to our channel for more short statistical